So let us do the simulation for the class B power amplifier right now, complementary symmetry type class B power amplifier right now. So before we do the simulation, let us have a discussion on power amplifier first, where we consider the public addressing system as an example, where I give a very weak signal as an input, and it will be amplified by the amplifier, voltage amplifier. It has like the gain of AV. So for suppose that AV is not enough, I will be keeping another voltage amplifier with the gain of AV2. So like that I will be keeping multiple amplifiers where up to which I need some strength. I could improve the strength. Okay. So but in the last stage where I need like one other kind of module where it has to deliver the maximum power for the loudspeaker. This is my load. This is my load. What I'm expecting is, so whatever that maximum signal strength that I got it, so that signal need to be delivered. Maximum power signal need to be delivered to the load. So for that what I do is, instead of like voltage amplifiers, now I will be using a power amplifier. So where I consider that power amplifier as a last stage, and I need to know something about the power amplifier, not in the conventional way where I was calculating the voltage gain. To measure the performance of this power amplifier, I have to calculate the efficiency. So what efficiency means is where the output power, what the power amplifier is able to deliver, right, with compared to the input power, how much he is able to take it. So based on the output power, how much he is able to deliver, by the input power, how much he is taking, I will be calculating that. I will be considering as a one parameter called efficiency. Based on that, I will be differentiating what kind of power amplifiers that I have. The same way, we have differentiated the voltage amplifier based on that output voltage by the input voltage, because it is a voltage amplifier. It is like a power amplifier, output power by input power is taken into the consideration as a efficiency parameter. So now coming to the efficiency, right, finally after we design a power amplifier, we have to find that efficiency. That is like a one track, we'll keep it aside. Now before going to calculate the power efficiency, first of all let us see how the power amplifier is made. So this is what my class B power amplifier, where like a PNP transistor and NPN transistor was connected. Let us have small discussion how we are keeping two transistors instead of one transistor. As of now we use it as a amplifiers. So if I have one transistor, for suppose like I have an employee E1, or we call him as a E1, where I need to do some job, where so suppose this is what my input signal need to be processed. So this is the first cycle, we consider is a day 1. This is the second cycle, consider as a day 2. This is the third cycle, consider as a day 3, D4, D5. Means I have 5 days work, I have it. I have to process that work for 5 days. So 5 days work, if I consider as the one day, this is my daytime work and this is the nighttime work. I'll separate like that, the entire work during the daytime and during the nighttime. So when it is a daytime and when it is a nighttime, that both work at a daytime and nighttime both to be done in the sense. So the employee where I keep it, when employee who I have it, right, I have to provide some kind of accommodation. I have to provide accommodation like in the general example point of view I can say. So I need to provide the accommodation because like during the daytime and nighttime I have to make him to do the work. So what happening is, to provide the accommodation I need to pay the rent. So most of the amount, most of the amount is wasted for like giving the salary along with paying the rent. So what I feel is, instead of going with the first case, I will be going with the second case, right? Where in the second case, the daytime work and nighttime work. So where I'm not using one employee to do the task in the daytime and nighttime. So what I'm trying to do is, I will be keeping two employees now. So employee 1 and employee 2. What I'm saying is, for the first employee, I'm asking him to do the job when it is in the daytime, and after that job is done, after the work is done, I'm asking him to leave. At the time, second person will come over here and will do the rest of the job in the night time. So while daytime work is done by one person and nighttime one done by another person, where I need not to provide accommodation for the employee, so that I will be saving that whatever that I am paying as a rent. So the same way, right? So whatever that transistor 1 I'm using, right? If it is processed for the first off cycle and negative off cycle, right? I have to make sure that I have to provide the accommodation, means I have to make sure the transistor need to be operated in the middle, so that positive off cycle and negative cycle will be processed by the one transistor. That's what we happened in the amplifier, voltage amplifiers. a common emitter kind of circuits. Now what I'm trying to do is I'm not interested in giving a biasing, right? Because of the biasing, most of the power is wasted. I'm asking that transistor circuit to operate over here. I'm not giving the biasing. So if I'm not giving the biasing, the transistor only conduct for only off cycle, it will conduct only off cycle. So remaining off will not be conducted. But I don't have any problem that first off cycle is conducted by one person in the sense, daytime work is done by the one employee in the sense, right? I have another employee will do the rest of the job. So that's why like instead of keeping one transistor in the conventional amplifiers, in the special kind of class B power amplifier, I will be keeping the person who do the job, right? That same kind of person, right? Who can do that complement kind of work, daytime work, like other kind of work like will be done by complement transistor. Like if it is a NPN, so we'll be keeping a PNP, right, to do the job at the night time. So now we'll take the same thing as an example over here, and the schematic, the diagram we have it for the class B power amplifier over here is, I will be keeping a NPN transistor over here and a PNP transistor over here. So when I give that work over here, I will be considering only D1 work over here. For the D1, I have a daytime work and nighttime work. I will be giving a positive off cycle and negative off cycle. So this is my considered as a positive off cycle, right? Positive off cycle, right? When I give a positive off cycle, consider as a daytime work. So when I give this kind of work, right, transistor T1, right, the current will be conducted like this because you give the positive cycle, so the current will be flowing over here. So when the sufficient current is going through the transistor will be conducted like a transistor will be coming out of the cutoff, so he will be active, right? So meanwhile, right, for the positive off cycle, this transistor will be turned on, this transistor will be turned off. So this transistor will be turned off, this transistor will be turned on. So now what happening is there will be sufficient current will be conducted over here like this, and it will be delivering some kind of power to the load. So whatever the positive off cycle what I give it, that what it will do is it will be making this transistor turn on and it will be conducting some amount of the current. But it is a power amplifier, as we need to know one thing is, so whatever that output power is delivered, finally what we are expecting is across the loudspeaker, we are expecting that whatever that input signal that we have, that same kind of thing like to be appeared. Means I have to generate like a positive off cycle when I give a positive cycle over here. Yes, it means when I give like input voltage over here, right, it will be conducting like a positive off cycle current over here. So beta times of that, beta times of like it is considered as a IB, it is considered as IB. So beta times of IB, it will be conducted as a collector current. So that beta times of IB current will be conducted over here means like the similar kind of signal because it is a like current control current device. How you increase the current, that increased current will be flowing. Decrease the current, decreased current will be flowing. Means what kind of that shape that we are giving over here, that same kind of shape will be conducted over here from the VCC. And we have to clearly understand that we are getting a positive off cycle over here, which is like a proportion of this one, positive off cycle conducted over here and delivered to the load, in the sense that the load is delivered with a positive off cycle. It doesn't come from the input. The positive off cycle is taken from him and delivered to the load. So here what we have to observe is the transistor is delivering the maximum power to the load, means so he is not taking any kind of power from the input. He is taking the power from the supply. The supply which is generating the current, that current will be in the form of like the peak voltage, the positive peak current. That current will be flowing across the resistance so that the positive off cycle will be appeared. The current into the resistor that will be forming as the voltage. So this is how like a positive off cycle will be delivered. So that is the job of the first employee. So the employee, what he has to do is he has to take a positive off cycle and a proportionate positive off cycle he has to conduct. So that positive off cycle, it should be conducted from the VCC. That is the whole concept of the transistor. T1 has to do it. So now we have to observe one thing. We have to calculate that efficiency for the first transistor, right? It means, so whatever that average current he will be taking, right? Average current he will be taking into average voltage he will be taking, that will be considered as a power average power or DC power, right? PDC power, that he will be taking as a input. That he will be taking as an input, right? The transistor like of NPN, transistor like NPN, he will be taking power of PDC is nothing but the average current he will be taking to deliver this much power, into average voltage he will be taking. So we need to calculate the average power, average current over here into VCC. Average voltage is nothing but on an average he will be giving that voltage of this one is a VDD, so 12 volts. So now I will be calculating over here 12 into I average, even we call it as a IDC, right? So this component is nothing but the power he is taking over here, and out of this much power, like how much power is delivered. That's what we have to calculate, right? In the similar fashion, right? In the second case, during the night time, when I give like a native off cycle, the transistor T1 will be off, like a T1 in the sense transistor NPN will be off, NPN will be off, and he will be on. He will be on. So now, how exactly like native off cycle we give it? That transistor also need to deliver that native off cycle over here. Native off cycle over here. Native off cycle need to be delivered in the sense there is a native voltage source which we have it ground over here. As we know, always current will flow from that high potential to the low potential. So here the ground itself considers a low potential, high potential. So that current will be conducted like this, right? So how exactly like that current over here it is varied, the same kind of current will be going through this one, right? So when the current is flowing over here, this is becoming plus and this is becoming minus. So that is how like you will be getting a native off cycle. So now if you combine both, right, loudspeaker is totally delivered with the positive off cycle in the daytime, native off cycle in the night time. So this kind of output you will be getting across the output. This is the load voltage, right? So what I will be doing is I will be calculating V average, VRMS, VRMS, and I will make it whole square by, if I keep it a RL is nothing but a loudspeaker resistance. So this will be called a total AC power which is delivered to the load. So now I will be combining the total thing and I will be telling you how you calculate the power dissipation and how you calculate the efficiency for that class B power amplifier is, right? So in the daytime and in the night time, right, the total period of like a total period of like one cycle, right? So there is a first transistor and after that a second transistor, both will be active and taking a power from this one and taking a power this one from this one. And now so total power is nothing but this much power he will be taking from the VDD, and he will be taking power around like a minus 12 times of, right? There will be I DC current, because like the current is going over there, so I will be keeping it as a minus notation. So minus of minus it will be becoming a plus. So 12 times of IDC I have to calculate. So totally there will be a power which is taken by the first transistor and second transistor is, so first transistor will take a power of around, so first transistor he will take a power of around, so first transistor he will be taking a power of around PDC, input is nothing but 12 times of IDC, right? He will be taking a power of first transistor, right? Second transistor is as it is, right? P DC input from the second transistor is 12 times of IDC. So the total power is nothing but 12 if you take it common, right? IDC of first transistor plus IDC of the second transistor. So I will be calculating the total power, right? So this is nothing but the total power he will be taking by the two transistors, right? So this entire thing will be considered as a input power. It will be considered as the input power, right? So now output power is nothing but the loudspeaker, how much he will be receiving the power, right? How loudspeaker what is receiving? Loudspeaker finally received with this kind of signal, right? So for this signal I will be calculating the P output, the power output is nothing but AC signal, right? So AC signal which is delivered to the loudspeaker, AC power is nothing but for this signal I will be calculating VRMS, right? Here I take a formula like a V into I for calculating the power. Here I will be taking a formula like a V square by RL. So V, because like I know the resistance of this one, V square by RL, right? So V RMS for the particular output load I will be calculating, and I know the resistance, I will be calculating both, and I will be putting together and I will be calculating the output power. So this one considers the output. Now what I do is input power I know which is taken by the two transistors, and output power I know which is delivered to the load. So if I put a ratio, that will be nothing but the efficiency of the power amplifier. So that is what final thing that we have to calculate for the power amplifier. That's what we do the simulation right now. So here we have a simulator. We have connected already that circuit diagram as it is we have. Let us see that how we do the calculations. Which full transistors will I'll take it, and NPN transistor I'll take it, and do the connections over here as it is. I'll keep my NPN transistor over here, and in the similar fashion I will be taking PNP transistor over here, and I will be keeping PNP transistor over here. Yes. So I do the connections over here. But while keeping my PMOS PNP transistor, what I do is I will be going with options and flip vertically. Yes, so that the arrow mark should be like this because the current is flowing in this direction. So that I have to make sure I have to flip my transistor such that the arrow mark should go like this. If the arrow mark is going like this into this one, from the minus VCC, the current should be flowing to the load, but it is not the case. So that's why like whoever like not flip the transistor like will not get the result. So make sure that they have to keep the transistor like this, and then do the connections. Then do the connections. And then simulate. So now, so here we can see that the DC current, I can see the DC current around like a 7.01 and a 7.74. 7.01, the DC current is, the DC current is, the DC current is 12 times of 7.01 plus 7.74 milliamperes, means 10 to the power of minus 3. So this much power, right? So what I do is I'll be taking calculating this power, input power. It's around like 12 times of 7.01 plus 7.74. Yes, this value 177. So now I can say it is around 177 milliwatts. 177 milliwatts, that is what the input power he will be taking. Two transistors combinedly will be taking this much power. So now coming to the output power, right? Coming to the output power. So he will be delivering that VRMS around 7.73 to the load. 7.73 to the load. So the output voltage VRMS 7.73. Yes, 7.73 whole square by RL. RL is around 470 ohms, right? I will be keeping 470 ohms as it is. So now if I take it the calculation value, (7.73) whole square by 470 ohms. So it's around like 127 millivolts. 127 millivolts. 0.127 you got it. We'll keep it as 127 milliwatts. So now total power efficiency is nothing but output power by input power. It's nothing but 127 by 177. Right? If you put it efficiency value into 100, we have to put it. So this value is nothing but 127 by 177. So this value is nothing but it is around 71.7 or something. 71.7. 7 efficiency, we got it. So we are expecting for the class B power amplifier, theoretically it will be the value of 74, right, or 78. That will be like calculated theoretically in the class through the derivation. So we got it this value when we do the practical simulations across the multisim. And one more thing that we have to observe is when we give that VCC as that input, we able to get that exact output waveform. But in another case, when we give that very weak signal, when you give that very weak signal, when we give that very weak signal over here, if you see weak signal in the sense strength of that 1 volt as the peak, if you simulate it, we can see that crossover distortion across that crossover distortion over this. So we are giving the positive off cycle and negative off cycle at the input, but the load is delivered with the only some portion of the output and only some portion of that positive peak and some portion of the negative peak. So over here, this portion is totally clipped, means this portion we can miss it output because like that much portion where it is needed for the transistor to come out of the cutoff 0.7 is voltage is required. So this transistor also needs 0. minus 0.7, right? So from that, so 0.7 over here and 0.7 over here, it will be like taken by the two transistors to come out of the cutoff. So remaining voltage of this positive peak and this negative peak will be appeared across the DC line, so that like you can see that across that crossing the DC line you can get the distortion, right? So the distorted waveform, right, distorted waveform where like crossout distortion, we can see it at the output in the class B power amplifier when we give that very weak signal. That's what one observation we have to do it finally. And one more thing that we have to eliminate the crossout distortion by some kind of biasing that we can give it. We call this one as a class AB power amplifier. It's not class B power amplifier. So what I do is in the class B power amplifier is what I do is in the class B power amplifier is so what I do is the class B power amplifier is I will be taking like a R4, R5, R4 network through which like I will be giving a biasing to the two diodes, so that these two diodes always will be in the forward. So once like diode is in the forward, it will be having a drop across this one is 0.7. That will be okay with that will be enough for this transistor to come out of the cutoff. That minus 0.7 is also enough for him to bring it from the cutoff, so that whatever the input signal we have, like without any clipping, without having any crossover distortion, we can get it output. So we can see this is how like a 1 volt peak signal, like a weak signal that in the previous case we give it, the similar kind of signal we give it again, but without the crossover distortion we are able to get it. So 1 volt peak, so peak to peak it will be 2 volts of input, and peak to peak of 2 volts as the output we will be getting once we give the proper biasing across the class B power amplifier through this branch. So once you keep this like extra branch over here, we can eliminate the crossover distortion. That is all about class B power amplifier where we got the distortion, and we can remove the distortion through the biasing circuit which we keep it along with the class B power amplifier, and we call it as a class AB power amplifier.